I decided to study abroad at the University of Otago in Dunedin, New Zealand for the entire year of 2015. This spanned the spring semester of my junior year and the fall semester of my senior year. I became involved in research and I completed the project presented before you today. Here's a picture of me at the gold mine, Springvale, that I studied. So why did I choose to study abroad? A lot of that has to do with the opportunities I had available at Juniata College. More than half of the students I met had studied abroad themselves, and this encouraged me to consider the option. I also signed up to live with an international roommate. I was paired with Fabiala Duma from Haiti, and we became extremely close friends. It was one of the best decisions of my life. She was abroad for the full year, and seeing her be away from home for 2 semesters showed me how useful it was to have that second semester in my experience, so I chose to study abroad for a year as well. Here's a picture of one of the science buildings at Juniata College. So then the next question becomes, why New Zealand? Being a geologist, New Zealand had obvious appeal to me. There's great academic programs and great natural geology there. They also have a myriad of environments close by, so I could experience different ecosystems. And of course, there's a great diversity in the indigenous population that I wanted to be able to experience. So then how did I become involved in research? Well, I signed up for a class called a paper in New Zealand at the University of Otago. It was called Independent Field Studies, but it wasn't like your normal class. Instead of having regular meetings, every student found a mentor to do research with. I was paired with Dr. Dave Craw, and he had this idea for this mine site, and I was a perfect candidate for him to do the research. Here's a picture of Springvale. So the things I want you to take away from these images are that there is a lot of rock exposed and that the topography is very unusual. There's a lot of slopes within a very small space. So then what was I doing there? My goal was to establish relationships between the geology, the vegetation, and the sediment chemistry. And the way that I did this is primarily by making maps. So I made maps of the geology, the vegetation, the water flow, and the sediment chemistry. With the sediment chemistry, there were 2 aspects I was particularly interested in. The first is pH, which measures acidity, although I put conductivity up there first. And then conductivity measures the salinity of the sediment. I also collected sediment samples and took them back to the lab for further analysis. I used an X-ray diffractometer to determine the mineralogy of the sediment and a scanning electron microscope to look at the texture of the sediment up close. So before I get into the results of my research, I first need to explain how the mining affected the landscape. So I'm going to use an example to help you understand the pictures I'm about to show. Imagine that you have a cake. You take a butter knife, you cut a slice of cake. Now you can see the layers in that cake, the different cake layers, the icing. Imagine you could do that to a landscape. If you cut through a landscape, you would be able to see all of the geologic layers underneath the surface of the earth. Geologists are able to make pictures that represent this, and we call them cross-sections. Here's a cross-section of the Springvale gold mine. The big green unit on the bottom is a mudstone unit. This kind of rock is highly impermeable to water flow. On top of it are a brown and an orange unit. Both of these represent rock slides coming off of nearby mountains. In the rock slides, there's gold. Gold is denser than rock, so it settled to the bottom of the rock flows and went right between the permeable rock slides and the impermeable mudstone. When miners realized this, they removed most of the rock slides to mine the gold, and the resulting landscape is much like the images we saw previously. There's a lot of variation in topography and a lot of exposed rock. The other thing I want to note right now is that even though they removed the rock slides, there were still remnants of those rock units, pebbles and sand, strewn in some areas of the site. These are what I'm going to refer to as mine tailings later in the presentation. So these are the maps. These are the crux of my research. And the black line on the outside, the weird shape, is the outline of the gold mine. We're looking down on the gold mine from a bird's eye view like you would in an airplane. The different colors, lines, shapes, and symbols represent different things, so each map has a different topic. The first one is geology, and then there's vegetation, water flow, and sediment chemistry. And for the sediment chemistry, this map is only for the conductivity. Now, while I think in terms of maps, I understand that most, if not all of you, do not. So I'm going to explain what these mean using photographs. Here's a picture standing on the mine site looking up at an outcrop of that barren mudstone that was exposed by the mining. Something you need to understand in the region of central Otago is that the climate is semi-arid. There's not a lot of rain. So the sun bakes and hardens this sediment in this mudstone over time. When it does rain, it erodes heavily this unit. It brings a lot of sediment downslope. The rain is also slightly saline in central Otago, as in most places in New Zealand. This is similar to the reason that the air smells salty when you're at the beach. Just being close to the ocean, which all parts of New Zealand are, puts a lot of salt into the rain. So when there are rain events here, not only is it pulling sediment downslope, but it's pulling a lot of salt downslope too. And then when it evaporates, all of the salt crystallizes at the bottom of these slopes, and we call these salty slope fans runoff fans. That's delineated by the dotted line in this image. What we found is that a few special kinds of plants called halophytes live in these runoff fans. They only are a few centimeters tall. They're really, really tiny, so they're hard to see at the scale of this photograph. There are two main species up on the diagram, and they only live in the runoff fan, only within those dotted lines. So this brings us to the conclusion of this part. The bare rock doesn't have any vegetation living in it. The runoff fans only have halophytes. And then you'll notice underneath of that, there's grass and bushes. All of the other vegetation lives in the mine tailings I mentioned before. So now we can see that each vegetation distinction is directly correlated with the boundaries of different rock units, different substrates. So now I'm going to use some graphs to help quantify some of that. The vertical axis on this graph represents pH, which again is a measure of acidity. A pH of 7 is neutral. Anything lower than that is acidic, anything higher than that is basic. The horizontal axis shows conductivity, which again is a measure of saltiness. The higher the amount of conductivity, the more salt is in the sediment. The red triangles represent sediment where halophytes grow, and the green diamonds represent sediment where other vegetation grows. You'll notice that there's a bit of a divide at about 1,000 microsiemens, which are units of conductivity. There are a few crossovers, but I don't have time to discuss the outliers, but the trend is pretty solid. Now let's look at a similar graph for sediment where nothing is growing. I subdivided these units to see if there's a trend, but there isn't, as you can see. There's, again, no trend with pH, but what's really interesting is that there's this divide that doesn't exist on this graph. There's bare sediment with conductivities where only halophytes can live, but they're not growing there. So then we were looking into why. So we went back to the mine site. I took sediment samples from each of the red circles, one where no plants were growing and one where only halophytes were growing. We examined them using scanning electron microscopy, which again helps see up close the texture of the sediment. Notice the scale bar in the corner of this picture, if you can see it. This picture is it's got 10 microns across for that scale bar. That's 1/1000th, or 10 10,000ths of a meter. So this is a very small scale. The sediment is extremely compacted, and the particles themselves are quite small. And this is the sediment in the bare outcrop. Now look at the sediment in the runoff fan. Particles are large, and they've got large gaps between them. The scale bar is even larger on this one. It's only 20 microns. So this uncompacted sediment is where the halophytes are growing, and that begins to make sense because when you think about plants and their root systems, the roots only go about as deep as the plant is tall. So remember how tiny those halophytes were? Their roots only go a few centimeters into the ground. They can't penetrate that bare mudstone that's being eroded. They can only establish root systems in this uncompacted sediment of the runoff fan, which also accumulates salt over many rain events and becomes incredibly saline, so that none of the other grasses or other species can grow there. So we've created, at this mine site, the perfect environment for these endangered species. So the results. We've established both mechanical and chemical controls on where the halophytes can survive. That's incredibly important because they're endangered, but native to New Zealand. So they contribute to the biodiversity of New Zealand, and they're really interested in how they can reestablish these kinds of habitats. And then we also established how different vegetation patterns are directly correlated to different geologic units and substrates. This is useful to know because then we can say that when you're doing mine remediation, you should incorporate different landscapes and different substrates to encourage the growth of biodiversity and to restore an ecosystem. I'd like to note that this is a case study. Most mine sites are not this clean, so to say. The most toxic thing at Springvale are elevated concentrations of salt. That is not the case for most mine sites. Most mine sites have heavy acid concentrations or are laden with heavy metals. For example, currently residing in Butte, Montana. Some of you may have heard of Butte as being nicknamed the richest hill on earth. There was extensive gold, silver, and copper mining here throughout the last 100 years at least, if not more. This was particularly productive during the first 2 world wars. They started open pit mining, which is what you see here. This pit is called the Berkeley Pit. When mining stopped in the 1980s, it became flooded. This water is incredibly toxic. It is acidic, it's got all sorts of heavy metals and all sorts of really nasty concentrations. Some of you might be able to tell there's a building in the distance on this photograph. It's a little hard to see, but there's a factory in this photograph for water remediation that should give you a sense of the scale of this open pit that has become a toxic lake. Some of you might have heard of Butte recently because we were in the news when migratory geese landed in our mine water and all of them died. Luckily, there are organizations like the Environmental Protection Agency, called the EPA, which remediate places like this. Butte is a Superfund site, so the EPA is going to dedicate resources to cleaning up our water, which, yes, we are concerned about it contaminating our groundwater within the next few years. The water levels have been rising over the last several years, and it's getting to a critical point. So again, most mine sites have problems more similar to this instead of Springvale. So Springvale was able to naturally remediate, but the toxins in the Berkeley Pit are more similar to what prevents remediation occurring naturally at other mine sites. Again, so Springvale is special. Here's a picture of generally what mines look like before they're remediated by the EPA and other useful organizations. This is what they look like after they're remediated. It looks much better. They flattened the ground, they added grass, it looks healthy. But then when you begin to think about what was there before the mining occurred, you can realize that we're not really restoring an ecosystem. We're not replacing what we took away. So we need to use biodiversity and ecological recovery during our mine remediation techniques, which isn't really something that is a focus right now. So why is biodiversity important? Well, we can't survive without it. Imagine if a disease came into that field and that disease attacks that species or 2 species of grass in that field. The field will die. But if a disease goes into the forest and attacks 1 or 2 species of trees, the forest survives. There's plenty of other species of plants, animals, fungi that support that ecosystem. The same is true of humans. There are numerous examples throughout history where one population of people meets an isolated and new population of people, transfers a new disease, decimates the population. Think of colonialists with the Native Americans. People are able to survive that because of their biodiversity. There are some people, some organisms that are naturally resistant. So biodiversity allows populations to survive diseases. So with this information that is applicable to mine remediation, what did I do? First, I wrote a nice long report for my class that my advisor sent to the New Zealand Department of Conservation because they're interested in how to restore ecosystems more than they were, but particularly the halophytes were really interesting to them. They knew they were there, they didn't really know what was controlling them. A lot of biologists work at the New Zealand Department of Conservation, so it was nice to have some geology to contextualize what was happening. I also presented at a mining conference, which was a great experience for me and for professionals to discuss, why was I advocating this form of remediation. And then I published my paper with my advisor and other professionals we consulted with. And on a more personal level, I was inspired and motivated to continue this kind of work and to think about these kinds of things. I was able, and I had the experience that I needed to continue with this. I was able to get into the grad school of my choice. I could not do this alone. There are a myriad of people who helped me out at all parts of this. You're up there, and you know who you are, so thank you. And thank you for listening.